Hello again. This is section 2.3 from the James Stewart Calculus Early Transcendentals book, and 2.3 deals with calculating limits of functions using the limit laws, and this is part 2 of this section. So recall from section 2.2 when we introduced the limit of a function that the two-sided limit, the limit of a function as x approaches a, the two-sided limit is equal to L if and only if the limit from the left, and that is as x approaches a from the left of f of x equals L, and the limit as x approaches a from the right of f of x also equals L. Otherwise, the limit will not exist. The two-sided limit will not exist unless the limit from the left equals the limit from the right. Good? So here, let's use that concept to try to find some two-sided limits and also involving absolute values. So in this case, you can, if you know the basic graphs of functions, like if you knew that the graph of the absolute value of x function is looks like a V. It's the line x equal to -1 on the left-hand side, and x equal to y, and on the right-hand side it is the line y equal to x on the right-hand side. And we can see here that the limit as x approaches 0 from the left of the absolute value of x is approaching 0, because we can see from the function outputs we are approaching 0 from the left, and the limit as x approaches 0 from the right of absolute value of x, looking at the outputs, this is x approaching 0 from the right, and our function outputs are approaching 0 as well. And so because the limit from the left equals the limit from the right, this implies that the limit as x approaches 0 of absolute value of x is also equal to 0. This function here has no output at x equal to 0, and the graph of this function looks like two lines coming from either direction. On the right-hand side, it's going to equal absolute value of it. So think of just building a table of values. If I had absolute value of 3 over 3, that's going to give me 1. So I'm going to have a graph that is the line y equal to 1 on this side, but I'm not going to have an output at 0, so I'm going to have an open circle. And think of just pick an arbitrary value on the left-hand side. Absolute value of -3 over 3 is going to still give me 3 over 3, which is still going to give me -3 on the bottom, it's still going to give me -1. And so when I have -1, I don't have an output at 0, but I am going to have the line x or y equal to -1. And I do have the definition of absolute value of x in a piecewise defined function that can also help you if you don't want to graph your functions. It can help you evaluate. So now let's calculate the limit, and from this graph I can see that the limit as x approaches 0 from the left of absolute value of x over x is going to give me -1. The limit as x approaches 0 from the right of absolute value of x over x, that's going to give me +1. Because the limit as x approaches 0 from the left does not equal the limit as x approaches 0 from the right, this tells me the limit as x approaches 0 of absolute value of x over x does not exist. That's a backwards E with a slash through it. Good. You could also consider, just like what I did before with 3 and -3, you can pick values very close to 0 from either end to also demonstrate without graphing. All right, so if I were to plug in, this one actually is a left-handed limit. This is a one-sided limit. So we only have to concern ourselves with values from the left. And I see, looking at this expression, I can factor out a 2 from the numerator, and I get 2 times x squared plus 5x plus 6. And over the absolute value of x plus 3. I notice that I can factor the numerator. Again, into x plus 3 over x plus, or times x plus 2, and I still have over x plus 3. And here, because I am approaching, and we do want to be able to cancel, because x plus 3 divided by x plus 3 is going to give us a value of 1, but is it going to give us a positive 1, or is it going to give us a negative 1? So it's kind of the same exact expression as the square root x over x, only we are shifting over to the left at negative 3, right? And if I'm approaching from the left, that means just think of values that are to the left of negative 3, so just pick one. So pick a test point. That will actually give you something. So what is minus 4 plus 3? Minus 4 plus 3 over absolute value of minus 4 plus 3 is going to give me a minus 1 over 1, and that's going to give me a minus 1. So I'm going to want to, when I cancel, put in a minus 1 here. And now that I've gotten rid of my problem point, because I would have gotten 0 over 0, I factored out that 0, that x plus 3, and absolute value of x plus 3. This is a left-handed limit, which is why I was using a left-handed point on as a test point. If I were a right-handed limit, I might pick 5, and then I would have a positive 1 factor. So now I can go ahead and substitute my value of minus 3 to get my value. So this is going to go to 2 times minus 3 plus 2, and that's going to equal 2 times minus 1, and we're going, and I still have the minus 2, right, because this together, right, we'd have 2 times minus 1 is minus 2, and negative 2 times negative 2 is going to give us 2, and that's my answer. Good. And finally, our, we could do these two. Determine if f as limit as w approaches 1 of f of w, determine if it exists. So we have a piecewise defined function. Again, you can graph the piecewise defined function if you want to, or you can calculate values. So, or calculate your one-sided limits. I see that we are calculating the limit as x approaches 1. So if I'm going to consider the limit as x approaches 1 from the left, I want to take values that are really close to 1, but that are smaller than 1 because it's coming from the left, right? So this is approaching 1 from the left, and here we're approaching 1 from the right. Good. So if I just take a look at items from the left, where is 0 in this range over in the expression? We have this value here, right? That's going to give me values. That's going to give me where my 0 is. So I can say the limit as x approaches 1 from the left of f of x, we're going to go to 1 minus 1 squared, and that's going to give me a 0. Next, I can take the limit as x approaches 1 from the right, and here I'm looking at, in a test point over here, maybe 2. So where would 2 be? 2 would be in this range for w bigger than 1. So I would say the limit as x approaches 1 from the right is going to go to 1 minus 1, right? Because we are putting in our value in that expression. And just like the one above, we were doing our zeros there. right? We're using those formulas. And what's 1 minus 1? That's also going to equal 0. Because the limit from the left equals the limit from the right, we do have that the limit as x approaches 1 of f of x is equal to 0. And I probably should have used w instead of the x's, I'm sorry. Determine if the limit as x approaches negative 1 for f of w exists. So again, I'm going to try the limit as, I'll try to do the w this time, and w approaches minus 1 from the left, and here we're looking at minus 1, and so this is approaching from minus 1 from the left, and on this side, it's the w's are approaching minus 1 from the right. So if I take something to the left of negative 1, I could be looking at a negative 2, and where is negative 2 up here? I see negative 2 in the w less than or equal to minus 1, and so this is just going to a constant, right? That's just going to go to the limit as w approaches 1 from the left, or negative 1 from the left of 1, and that's just going to give me 1. And the limit as w approaches minus 1 from the right, I'm looking at maybe a 0, and where is that? That's going to give me this one in this range, because that's where 0 is, and it's where I'm closest to the minus 1. And so the limit of my f of w is going to go to 1 minus 1 squared, right? Because I'm plugging in my value of minus 1 into where my w is. And I end up with 1 minus 1, which is equal to 0. So because the limit as w approaches 1 from the left, negative 1 from the left does not equal the limit as w approaches negative 1 from the right, we see that the limit as w approaches minus 1, the two-sided limit, does not exist. Right? Good. And you can verify by graphing its piecewise form. Finally, we have what is known as the Squeeze Theorem, which is kind of nice, and it's really good to see from the graph. If we've got, let's just say, for instance, our f of x is, and here we've got some really funny things. So here in this case, we've got our f of x is below g of x, and g of x is entirely below h of x, right? Good. So if the limits of h of x and f of x actually equal each other, this is what our squeeze theorem is, then the limit of g of x is also going to equal L. And that you can tell from the graph if we always have that. So for values that are really close to A, we can see here that g is squeezing through that limit. Good? So it's almost like we're saying then the limit as x approaches A of f of x is less than or equal to the limit as x approaches A of g of x, and that's going to be equal or less than or equal to the limit as x approaches A of h of x. And if these guys are equal, L less than or equal to the limit of g is going to be less than or equal to L, then by that compound inequality, the only answer that g can be is equal to L as well. Good. So here we have two examples, and the bottom one is the fun one, and it does require some fundamental trig facts. But this one, limit as x approaches 4 of f of x, and we have, that's what we need to find. And we note in this case that 4x minus 9 is less than or equal to f of x, and that's less than or equal to x squared minus 4x plus 7 for all x's bigger than 0. And since x is equal to 4 and 4 is bigger than 0, we can apply the squeeze theorem. So my limit as x approaches 4 of 4x minus 9 is going to give me less than or equal to the limit as x approaches 4 of f of x, and that's going to be less than or equal to the limit as x approaches 4 of x squared minus 4x plus 7. And if we're going to evaluate our limits, we go ahead and substitute the value of a into our expression. And so we get 16 minus 9. And 16 minus 9 here is 7. And that's going to be less than or equal to the limit as x approaches 4 of f of x. And the limit as x approaches 4 of x squared minus 4x plus 7 is going to go to 4 squared minus 4 times 4 plus 7. And that's 16 minus 16 plus 7, and that is also equal to 7. And so since these guys are the same, that tells me the limit as x approaches 4 of f of x is also equal to 7 by the squeeze theorem. And finally, with prove that the limit as x approaches 0 of x squared times sine of pi over x is equal to 0. Okay, so we can start off with the limit of pi divided by x is less than or equal to 1, and it's also bigger than or equal to minus 1, right? Because we've got our function sine doesn't go above 1, and it doesn't go below negative 1. Good. And this function would not be defined at x equal to 0. Good. But we do know that this is the case. So then we can actually apply by multiplying by x squared on all three sides. So we can multiply by x squared, multiply by x squared, and multiply by x squared. So we would get minus x squared less than or equal to x squared times sine of pi over x less than or equal to x squared. And then we can say the limit as x approaches 0 of minus x squared is going to be less than or equal to the limit as x approaches 0 of x squared times sine of pi over x. And that's going to be less than or equal to the limit as x approaches 0 of x squared. Usually when you have a trig function and it's multiplied by something in your limits, and you don't get, because if I plugged in 0, I'd get pi over 0, and sine of infinity does not, that limit will oscillate back and forth between positive and negative 1, so our limit as x goes to 0 would be infinity, and we wouldn't have an infinity times 0 is an indeterminate product. So that's a topic for another section, another chapter, L'Hopital's rule. But here we can apply the squeeze theorem, and we can apply our limits on the left-hand side. The limit as x approaches 0 of minus x squared is going to be minus 0 squared, which is going to give us 0. And the limit as x approaches 0 of x squared is going to go to 0 squared, which is also 0. And so by the squeeze theorem, the limit as x approaches 0 of x squared times sine of pi over x is also equal to 0. All right, so that concludes part 2 of section 2.3, calculating limits using the limit laws. We also have here the squeeze theorem, and we've got some examples involving absolute values and one-sided limits. So next up will be the precise definition of the limit, which might be a bit challenging for some people, but look forward to it. Take care.